Okay, and this is based on chapter 16, superconducting device. So let's recap. This is some important fundamental concept. What is a superconductor? When the temperature goes to 0, when it is reducing, there will be a point that is resistivity rho will suddenly reduce significantly, right? This is resistivity, right? And within experimental accuracy, you will see that it is like almost 0. But this is not the definition of a superconductor. Superconductor has this behavior, but more importantly, it is that it will expel all magnetic field inside it, and that's called Meissner effect. For example, when you are at normal state at high temperature, larger than the critical temperature, if you try to reduce the temperature to 0, if it is a regular perfect conductor, which means it has 0 resistivity, the magnetic field will stay inside. But if it is a superconductor, it will all got repelled. And that is the principle of the magnetic levitation, right, for the high-speed train, high-speed railway train, right? So this Meissner effect is another test for superconductivity. And we mentioned three critical quantity: the critical temperature, critical magnetic field, and critical current density. Or if you know the area, is the critical current. Basically, what you say that if your temperature, right, is less than these three quantity, is less than critical temperature, you have superconductivity. Or let me say in opposite way, because they all need to fulfill at the same time. If your temperature is larger than the critical temperature, you will lose superconductivity. If the magnetic field trying to penetrate into it is larger than the critical magnetic field, you will lose superconductivity. And if your current density is larger than the critical current, you will lose superconductivity. These are all easy to understand because in the sense, superconductivity is something to make you attain a very special state. If you have some high energy situation, such as high temperature, high magnetic field, high current, you will break the superconductivity. So I hope you to be aware of this. Okay, any questions? Okay, now, then why there is superconductivity, right? So we won't go into details, but we just look at its properties. The superconductivity can be explained by this Bardeen-Cooper-Schiffer's theorem, BCS. So whenever you see BCS, you understand it is related to the superconductivity. And Bardeen is the one who got 2 Nobel Prizes, one for inventing the transistor, another is for explaining the superconductivity using BCS theory, right? So what happens when a metal is in superconductivity? We just accept it. It is because it bonds 2 electrons together with the opposite spin and opposite momentum. They become one entity. How can that happen? You can read the book, explain a little bit, or Google. It's mediated by the phonon, which is the lattice vibration. Basically, you can think of the lattice is positive charge, and you kind of bring 2 electrons closer together, and then they become a Cooper pair. Okay, and this is called Cooper pair when we bond the 2 electrons together. Let me see. I have the picture later. Maybe I'll explain that later. But what is the main point? What is the spin of electron? We have spent half of the semester talking about that. What's the spin of an electron? Spin of electron, or it is half, right? It is half. But what if you have 2 electrons spinning in opposite direction, combining together, has a whole entity, just like a positive charge and negative charge combined together? What will be the spin? Spin 0. So that is very important. Cooper pair has spin 0. Now that is something we can review for physics, but it's good to learn if you don't know this yet. You should recognize that, okay, there's one type of particle called fermion. Fermion has long integral spin. Means that its spin can be half, 3 half, 5 half. Okay, they have long integral spin. Integral, can I not say long integral? Huh? Long integer spin, not long integral. So maybe my English issue. I follow you. But anyway, you guys understand what I mean. Either 1 half, 3 half, 5 half. Okay? Long integer spin. Now, for example, electron. Electron has a spin equals to half. Right? We talk about that. So what's so special? They will obey Pauli exclusion principle. If you remember from your chemistry, it means that you cannot have the same electron, and you cannot have 2 electrons occupying the same state, right? Meaning that you cannot have the same quantum numbers. So for example, you cannot have 2 electrons occupy at the lowest energy level. But then you may ask, isn't that we can have 2 electrons in hydrogen at the lowest energy level? Are they occupying the same state? Actually, no. Why? Because one spin up, one spin down, right? So if we take that spin into account, they are at different states, right? So the main point is that it obeys Pauli exclusion principle. Now, if you go through the math statistics, which we will not prove, this is not the purpose of this class, it follows the so-called Fermi direct distribution. And many of you, should be all of you, I mean, maybe not all because we have some people not from EE and physics. But you have taken solid state physics, right? You all know that the electron follow Fermi direct statistics. So you have different energy level. The probability of the electron to occupy energy E equals to 1 over e to the power E minus mu divided by kT plus 1. Okay, where, let me rewrite. Where E is the energy of the electron, right? And mu is the so-called chemical potential or Fermi level. Is this okay? Right? Just to recall, if you have not learned this before, no need for this class. But at least I hope that you can tell people you understand electron. Just like this classroom, if each chair is a state, you can only fit 1 people. This is like Pauli exclusion principle. If she occupies this seat, you need to occupy other. Okay? You cannot sit on the same chair. Now, then, naturally, if it is long fermion, what would that be? It is called boson. And it, of course, has what type of spin? What do you think? Integer, yeah. So, which means its spins can be 0, 1, 2, 3, 4, 5. And Cooper pairs, which is 1 electron spin up plus another electron spin down, it's like chemical reaction, becomes a pair of electron which has 0 spin. Is a boson. So this is very interesting. You see, it's supposed to follow a certain statistics. But now, because of the low temperature, they got paired up. and they have zero speed. You treat it as one particle, one particle, right? And what does it do? It will obey, instead of Pauli exclusion principle, right? Or let me don't call it obey. I should say follow, right? I don't want. There's no other rule. It will follow, not follow. Why you guys don't tell me? It will follow the so-called Bose-Einstein distribution. Right. So what does it follow then? It says that the expected number of particles at E, at energy E, I just call FBE of E, equals to 1 over, it is almost the same, E minus mu divided by KT, but minus 1 instead of plus 1. So what is the Bose-Einstein condensate or distribution? Right now, if this chair is empty, this time we're not filling people. We may be filling books. You can put a book on the chair. If you have more book, you can continue to put on the chair. And it's unlimited. So there's no Pauli exclusion principle. Both books have exactly the same state. They occupy the same chair. Right? The states may be talking about in the country of US, in the state of California, in the city of San Jose, in the school of San Jose State U, right? In this engineer building, on this floor, in this room, at this fifth chair, they all have exactly the same state. They can have exactly the same state. Now, if you look at this equation, you see what? We usually set, let's just set mu equals to E log, which is the ground state energy, right? For any system, you must have a ground state, the lowest energy that you have. So if the temperature is very small, then let's say E is a little bit larger than mu, and temperature is very small. This one will still be 0. Unless E equal to E naught, then this is 1. Then you have 1 minus 1. Here is just telling us that FBE, the number of particles you can occupy is infinity. You just can put all, if you are at absolute 0 temperature, you can put all the particles in the same state. Make sense? Again, you don't need to understand this equation, but it's good to learn. We won't test this, right? Maybe assignment or whatever. But I probably won't have this in the assignment. But the most important thing is, remember, electron obey Pauli exclusion principle. You cannot occupy the same state. So you don't have electron laser. Boson, like Cooper pair, or light, photon is a boson. So you can have light laser because all the light, all the photon can have exactly the same state. Same wavelength, same momentum, same direction, same energy, and you shoot it together. That's why laser is so strong, right? So same here, but this is in solid state. The Cooper pairs is a boson. So you can put them in the same state. And what does it mean? Yeah, the solid state is a very complicated system, but it must have a ground state, right? You solve everything, eventually you find the ground state. And in this ground state, you can put as many Cooper pair as you want together. So they are just people say like a marching army. They all march coherently, and it becomes a macroscopic object. Think about that. If you have many people walking on the street, it's probably difficult to describe all these people together. But now it's an army. Everyone has the same height, same weight, the same way they March. Actually, this is just a macroscopic object. I don't need to describe individual people. This 1 million people is a macroscopic object, right? So that is the point. They will all described by the same wave function. First thing, okay? And what would be that wave function? Right, so it is a quant. Yeah.
Sorry, in the previous slide, you said it says.
They do, yeah. It doesn't come to this picture, but in the formalism, they have the opposite momentum also for the Cooper pair. Yeah. So you know, this is not talking about particle, right? It's a wave function. So like in solid state physics, you have the wave vector. So yes. Yeah. So again, we agree this is a quantum object because it's electron, and electron combined with electron is also a quantum object. So it has a wave function, right? We can describe it as a wave function. But I have 10 to the power 23 of them per cm cube, having exactly the same wave function. So just like I said, the marching army, now I only need to describe when they lift their left hand, at what angle, at what time. Then I describe the whole 1 million people, right? So same as this here. The wave function can be written as this. What does it mean? It means they should have the same phase, right? I hope that is not surprising to you. Now I describe all the Cooper pair with a phase. But I already said that they have the same state, so they share the same phase. I only need one phase parameter to describe this whole thing. Make sense? Yeah, if you're still thinking they don't have the same phase, then they are not occupying the same state. Right? Then what is NS? NS, think about this. When you try to do the measurement, right? Maybe I better do this. What is the square of this wave function? It's equal to NS. It's telling me what is the probability of measuring the electron. And of course, this is in the order of 10 to the power 23 per cm cube. This is the number of electron I have per cm cube of metal, right? This is the typical number. If you forgot, the density, number of atom per cm cube is about 10 to the power 23. Just take this for granted. So the number of electron is also in this order. Yeah, Cooper pair divided by 2, still in this order. The main thing is just to say that I came up with this phenomenological equation, which is pretty accurate. And actually, in the early stage before BCS theory, people use this one like the London equation, if I did not say it wrong, if I'm correct. Something like this to derive the superconducting behavior, right? But there's no proof. This is just phenomenologically. Yeah. Okay. So the main point is this. This is the wave function of the whole object. So now you give them a metal, and it is a superconducting state. If it is not transporting, no current, I can use this equation to describe the electron pretty well. That's the first thing. And that's why we say this is a macroscopic quantum object. Is that okay? Now, here I have a better picture, right? We say that, okay, spin half plus spin minus half becomes spin 0. This is the electron. And this becomes the Cooper pair. But based on this, you see that I have arrow going from left to right. This is just like chemical reaction. Two hydrogen combined together become hydrogen atom. Hydrogen atom can dissociate to two hydrogen atoms also. I mean, hydrogen molecule can dissociate to two hydrogen atom also. So you can go to left, go to right. What separating them is a barrier, an energy gap, right? You need energy in order to break the Cooper pair. So energy gap is delta, but you need 2 delta to break a Cooper pair. Because you have 2 electrons. Okay, this is just the definition of delta. That is the energy gap. But when you break it, you break 2 electrons at the same time, so it's 2 delta of energy. Okay? And after you broke it, this is called the quasi-particles. So when you read literature, sometimes they will say quasi-particle contamination causing the charge noise in your superconducting qubit is talking about this. If you have like absolute 0 temperature, you are not going to break it. If you don't have quasi-particle, then definitely your charge noise will be less. Okay, that's first thing. Second thing is this delta is temperature dependent. And you can find it from the literature. It's about 1.764 times KTC. Okay, we also take this for granted. Again, remember what is TC? Critical temperature. It's the temperature that you are not in superconducting state anymore. So here it tells us that if you have a larger critical temperature, for example, niobium is about 10 Kelvin, then you actually need more energy to break the Cooper pair. Means Cooper pair is more stable. If you have aluminum, I forgot, maybe 2 Kelvin or 1 Kelvin something, then you actually have like 5 to 10 times less energy to break the Cooper pair. Which also makes sense because larger critical temperature means going to higher temperature, I'm still a superconductor, right? It makes sense because you cannot break the Cooper pairs. Once you break the Cooper pairs, they are fermion already. You will lose the superconductivity, right? But the point is, even you are still in a superconducting state, you could have some reaction that you have some quasi-particle because this is thermostatistics, right? Yeah. Okay, that's a good point. What's the application? Actually, I think one possible application is as a sensor. So, for example, you are in superconducting state, you create a circuit, then you have no voltage drop, right? You have you have current just going forever, and they use this to detect, for example, radiation from the cosmic radiation, radiation, and then they may create a Cooper pair, a quasi-particle, and also locally they might make it become a normal state. Then suddenly you have a resistance, and then you use that to detect. And this is also used, some modified version used in optical quantum computing. So for optical quantum computing, you always need to detect the photon because they base on photon to decide the result, right? Whether you have photon coming in. Like for example, they have this Hurrow photon, they actually have a pair. You never know when a photon is emitted. So how do you know when to get the result? But they usually have they create 2 pairs. And then one will be like Hurrow. So once you trigger me, I know a photon has been emitted, then I start tracing it and do the computation, right? Or get the result, right? And how do you detect the photon? So they use this superconducting nanowire. That is one approach. Instead of using the so-called Geiger counter, right? Geiger counter is used every launch, you do the trigger. It's a PIN diode reverse bias to when your photon go in, you generate electron hole pair, and then you ever launch and you know that there's a photon just came in. But it also has false detection, right? Because even with no photon, there's a possibility that you can generate electron hole pair, and then you thought that there's a photon. So yeah, so I thought too far, but this can be a sensor. When you break the superconducting state by breaking to quasi-particle, you create a resistance, and then you can detect that there's a photon or a particle. Yeah. 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 If you have a magnetic field greater than the critical magnetic field, then you cannot get superconducting state even at 0 Kelvin. So here I actually did not go to details, but let me maybe now draw it. It actually would depend on each other. For example, you have a temperature here, you have the magnetic field here, and this is the critical magnetic field. This is the critical temperature. And then you will have a curve like this. Here is the normal state. Here is superconducting state. So you see that if I am at absolute zero temperature, I can still be at superconducting state if I am smaller than the critical magnetic field. But if you're actually not at absolute, let's say you go up to here, you actually will fail even before the critical magnetic field. Do you see that? So just like what you just said, if you exceed critical magnetic field or just at critical magnetic field, you need to keep your temperature at zero. Otherwise, it won't be superconducting. So you need to fulfill all of them at the same time, and then you have this constraint. Okay? Which makes sense, right? Because all of them try to make it a normal state. Now you have all of them at the same time, then you cannot get to critical for all of them at the same time. Okay? Okay, good. So here introduce some quantities. This one will be useful. We might not use in this class, but this is useful. Actually, we might. I did not teach that last time. I may teach it this time. We might use this to calculate the critical current. Not critical current. Use this to calculate the normal resistance, and thus the critical current. Yeah, I kind of messed up the equation, but it will be useful. Okay. Okay, so now we learn about superconducting state. Now we go to Josephson Junction and Josephson equation. Josephson Junction is very easy. If you show this to any undergraduate who had not learned about this, and what would you call this structure? Aluminum oxide, aluminum. What is structure? What type of device is this? Metal? Huh? Exactly, just a simple capacitor. So Josephson Junction is just a simple capacitor. But it won't work as Josephson Junction if it is at above the critical temperature. Okay? So it is a Josephson Junction when you have a superconductor on both sides. Right? So you need to cool it down so it becomes a superconductor. At the same time, the insulator, we did not say that, but your insulator need to provide a so-called weak link. How can you link two metal or link the work function in two metal together if it is an insulator? If it's an absolute insulator, you cannot link them, right? You need to be thin enough to allow quantum tunneling. Okay? So, but you cannot be too thin also, because for the theory we are going to use. So, right, to allow quantum tunneling. Okay? So basically that's it. So a Josephson junction is just a superconductor, insulator superconductor, but with thin enough, but cannot be too thin, right? And this is the typical fabrication. My book, I have more detail about how you manufacture, because you don't want to break the vacuum to contaminate it. So there are two common methods. But anyway, after fabrication, your goal is to have aluminum at the bottom, oxide separating the top aluminum. Okay? So it is very easy. But now we can use what we just learned. I have two regions. One is region A, region B, right? Isn't that I say that this one is a superconductor, but it is a group of Cooper pair. They occupy the same state. So I describe the whole thing with one wave function, psi A, right? And we just say that psi A equals to square root ns. Instead of ns, and we put na, which is not important in this equation. E in our class, I phi A, right? It has a phase, phi A. And similarly, I would have psi B, because this is just another piece of superconductor. I have psi B equals to square root NB, e to the power I phi b. Okay. Now the most important thing is that now you need to accept it. Of course, there are more rigorous derivation, and this is very simplified. But of course, phi A doesn't need to be equal to phi B, right? Because they are separated. They are not the same piece of metal. So we define a quantity called phi, which is the phase of this Josephson junction. We call it phi A minus phi B. This is because the physics of Josephson junction depends on the difference of the phase of these two terminals. And I hope that now you can appreciate why this is quantum. Because when you study electronics, classical electronics, the phase difference never contribute anything to the equation in electrical circuit. You won't say that, how to say, this voltage and that voltage has the current will depend on the difference of the, maybe that's not a good example. Anyway, I take it back. So, but the phase, we're talking about the phase. Actually, the reason I take it back is because I don't want to relate you to the phase of the voltage, which is real, measurable. The phase, we're talking the current voltage relation, the imaginary number, right? Because the phase definitely is important. But the phase here is not this phase. If you remember, this is the phase of the quantum object. And isn't we say that they are not observable, right? Because you do any measurement, the phase doesn't matter. And indeed, it doesn't matter, right? But here you see that the difference will matter for their current. So that's why you see that it has a quantum effect over here. Is that okay for this definition? Right, so this is something you need to memorize. And when people talk about the phase of the Josephson junction, it is the difference of the phase of the two wave function. Then it's easy. We are not proving it, so that's why it's very easy. There is two Josephson equations. So what are they? The first equation says the current going through this device equals to IC times sine phi. Okay, IC turned out to be the critical current. What is critical current again? Thank you. The largest possible current that is still in superconducting state, right? You can try to pump a lot of current to it, then it will leave the superconducting state. We earlier just talked about current density, but here is the current. It means you just multiply the current density by the cross-section area. That is the current for this superconducting. So you also see that if I try to design a Josephson junction in the future, if I want to have a larger critical current, all I need to do just increase its area. If I want to have smaller critical current, I reduce its cross-sectional area. Okay? But this is very interesting. The current depends on the phase difference, and it's sinusoidal. Okay? We take it for granted. It has a second equation to relate the voltage to phase. It says that partial phi, partial t equals to 2e VAB divided by h bar. So you say that if you apply a voltage across this capacitor, Josephson junction, your phase will change. It changes at a rate proportional to VAB. Like a transistor. But transistor is three terminal, so yeah, usually when you say transistor, you have amplification. But yeah, definitely it's not a simple diode, right? Yeah. Now here let's introduce a quantity, which is called, maybe I put it in the next slide, that will be better. Yeah.
Can you explain the second one?
Say again?
Can you explain the second equation?
Okay. partial phi, partial t, that is the rate of change of the phase, Josephson junction phase, right? Is proportional to the voltage across this Josephson junction. This is E, elementary charge, and this is reduced Planck constant, right? So here let's divert a little bit, talk about a quantity called magnetic flux quantum. So it is labeled as phi naught, okay? And it's defined as phi naught equals to h divided by 2e. It's based on fundamental constant. So this is the minimal magnetic flux you can have, right? We did not study what, you can have in a loop. We did not study carefully about what is magnetic flux. I assume you know, but basically flux, right, equal to the magnetic field times the area it goes through. Am I right? Forgot about this, right? So can you reduce it to almost zero? No, there's a quanta. The basic quantum is h divided by 2e. That's first thing, okay? And of course, I can divide the top by 2 pi, divide the bottom by 2 pi, right? Then this gives me 2 pi h bar divided by 2e. Then I define another quantity, phi naught dash. This one, I call it reduced magnetic flux quantum. So based on all we discussed so far, what is the reduced Planck constant? Do you know? How is it related to Planck constant? Reduced Planck constant? Yeah, Planck constant divided by 2 pi. So reduced magnetic flux quantum, what will you guess? It must be the magnetic flux quantum divided by 2 pi. Yeah, like what you said. So, do I do something wrong? So it is equals to h bar divided by 2e. Yeah, because this guy divided by 2 pi, that's h bar divided by 2e. Right? So the main thing here is that I hope you be careful when you read the literature. Sometimes they just exchange the label, right? Sometimes they call this reduced flux quantum. So you need to be careful. There may be a difference in 2 pi. Then let's revisit the second equation. JJ second equation. Right? What does it say? Partial phi, partial t equals to 2e v ab divided by h bar. Right? I copy it. And trust me, I copy it right. And based on this, of course, this is equal to VAB divided by the reduced magnetic flux quantum, because h bar divided by 2e is phi naught dash. Okay? Or if I really want, I can say this is 2 pi VAB divided by the magnetic flux quantum. So you will see different equation in the literature or you read books. Just be careful, right? But anyway, the most important thing is that the rate of change of the flux is proportional to VBA divided by reduced magnetic flux quantum. That's the second thing that I want to show you, that we introduce reduced magnetic flux quantum into the second Josephson equation. Okay. Now, then the third thing we want to investigate is, now I see that VAB equals to phi naught dash partial flux partial t. right? So let's recall classically. Do you know a voltage will be induced if you have a change in the magnetic flux? Right? In a coil, if the magnetic flux change, you will induce voltage. Partial flux, partial T. Do you see they are very similar? Why it is similar? Because what if I put this into here? I put phi, and then phi dash, the whole thing, partial T. Right? So looks like this is the flux, right? This guy, phi, the phase, this is the phase times the reduced flux constant, right? Which is the phase, let me call it JJ phase. JJ phase times the reduced flux constant, quantum. Behaves like magnetic flux. But the main point is here. This magnetic flux, right, will cause, this is due to the inductance and magnetic field. This magnetic flux, the reason we have this is because we try to have this inertia, we try to avoid the change of magnetic flux, and that's why we will create this magnetic field. And here, we also to try to against the change of this associated magnetic flux, but this magnetic flux is not due to the real magnetic field, right? This is due to what we call the kinetic inductance. Should I talk about this now? Because in superconductor, it has no resistance. So if you want to change the current, it has a very large inertia. You need to revert it, you need to apply a big force to change it. And that is the so-called kinetic inductance. In your regular design, you also have kinetic inductance. But because it is at room temperature, it will die out easily through scattering. And that's why your geometric inductance will dominate. But in superconductor, the kinetic inductance usually dominates. Okay. So this part may be, I don't say it well, but a little bit confusing. But after all, what do you need to learn? Magnetic flux quantum. You agree that there's a magnetic flux quantum that is h divided by 2e. That is the minimal, related to the minimal magnetic flux you can have in the loop. And it depends on universal constant h and e. So so that's why we can write the second Josephson Junction equation as VBE divided by phi naught dash. And finally, we show that the phase times the reduced flux quantum act like the magnetic flux in a regular inductor in Josephson Junction. Okay, so just remember phase times the reduced magnetic flux quantum will give you something like the magnetic flux. Although it is not a magnetic flux, but it has a behavior like the magnetic flux in a regular inductor. Any questions? Maybe pretty confusing, huh? Yeah.
So all like possible find how they stay. But do we even care about how they
We care about the difference. Difference, yeah. Individual is not important. Yeah. So your question actually lead to here, right? So let's look at the JJ equation. We have the equation, then what does it mean? For example, case 1, when let's say I apply voltage equal to 0, it means there's no voltage bias to the Josephson junction. Then what does it mean? Partial phi, partial t equal to 0 divided by phi naught dash, right? Which is VAB divided by reduced flux quantum equal to the rate of change of phi, right? Then it means what? Phi is a constant. Okay? The phase difference is a constant. So what will be the current? Current equals to IAB, IC times sine phi, right? Which is a constant, right? So what will happen to the current? Just some number, very good. This is the current as a function of time. It's just a constant. So I apply no voltage to Josephson junction and have a constant current. Does that make sense? Now you think carefully, actually makes sense. Because it's a superconductor, right? Of course, you need to initiate it with some current, right? Once you have current, it just runs forever because it's a superconductor. But of course, it's not that straightforward because we actually have an insulator in between. People all agree that if you have a ring of a superconductor, it will just run forever. But now you have insulator. It still just run forever because of this tunneling. Yeah? So that is something you cannot expect right away, right? So this is not very interesting, but probably you will find something more interesting now. What if VAB equal to a constant? We don't even say that it is, let me just call it V0, maybe. A constant. Then we go through the equation. Partial phi, partial t equals to V0 divided by phi naught dash. Then it means phi equals to, you need to do integration on it, right? Equal to V0 divided by phi naught dash dt, maybe from 0 to t. What I'm doing? Yeah. But V0 is constant, right? So this is just equal to what? V0 divided by phi naught dash times t. Yeah? So this is the plot of phi as a function of time. I'm talking about the phase. Right? It has a slope of 1 over the reduced flux quanta. So so what does it say? It says that if I apply a constant bias across the Josephson junction, their phase difference will linearly increase. And when actually this is V naught divided by phi naught. Okay, it will linearly increase. And then what does it mean to the current? IAB equals to IC times psi phi, right? But what is phi? We just prove it. Equal to IC sine V0 divided by phi naught dash t. So I have a constant voltage across the Josephson junction. Its current actually will oscillate. It will provide you an AC current. So this is T, this is I, and you get something like this. And this is the peak, IC. You cannot go beyond IC because then it loses superconducting state. Right? So here is assuming it is in the superconducting state. Now, I'm using the reduced flux quantum. Right? Now I want to go back to the flux quantum. Reduced flux quantum, the difference is that I have 2 pi, so when I pick the 2 pi, V0 divided by phi naught, because phi naught dash is phi naught divided by 2 pi times t, right? Let's compare this to a regular equation. Sine 2 pi ft. Do you see that? If I have a sinusoidal signal with frequency f, it is sine 2 pi ft. I think I'm right, omega t, right? And this is 2 pi this guy times t. So what does it mean? It means it oscillates. The frequency, this frequency equals to V0 divided by phi naught. Okay? And then I can continue to show that f divided by f0 divided by V0 equals to, because phi naught equals to h divided by 2e. A lot of math, but after all, it tells us what? The voltage relationship to the frequency is just equal to, or frequency divided by the voltage is just equal to 2e divided by h. And that gives a very important quantity, is that how do I define what is 1 volt? In the past, they used different experiment to define 1 volt. Define 1 volt is not easy because you need to make sure you can reproduce in every laboratory, whether it's on the Earth or on the Moon, right? Now this is used to define 1 volt. Because you see, Josephson Junction equation has nothing to do with material. It did not tell you how thick the insulator has to be. It did not say how good quality it has to be. As long as you successfully fabricate a Josephson junction, you follow the Josephson equations. And if you apply 1 volt across it, then the frequency is going to be 2e divided by h. So all you need to do is to measure the frequency, which can be done very accurately nowadays. And then you also know what is the electron charge, what is Planck constant, particularly E and H is invariant throughout the universe, is constant. So I can define my volt. All I need to do is do this experiment, fabricate a Josephson junction, although it might be different from the other one in South America. But when we do the measurement, we apply a voltage, try to get a certain frequency. And this is given by 4.83 times 10 to the power 14 hertz per volt. This can help me to define the voltage, right? I tune my voltage, of course, so that the oscillation is at 4.83 times 10 to the power 14 hertz. Of course, I'm not going to use 1 volt. I may use 1 millivolt or 1 microvolt. Right? So I go to the gigahertz regime, I measure the frequency. Then I'm sure that my voltage is the same as the guy doing experiment in South America. And then based on this voltage definition, we calibrate our equipment, we do more sophisticated experiment, right? And we are sure that we are using the same voltage. Because we are sure that E and H is the same in North America and in South America. And I'm also confident about the measurement of frequency, which has a lot of elegant skill to measure them accurately. Okay? Okay, good. So now we have this Josephson junction, right? You understand the equation. But after this, for the purpose of this class, is that we want to use this to define something called Josephson inductance. Like first of all, we need to recall what is a regular inductor. right? It is V equal to L di dt. You change your current, then you get a voltage. The ratio is L is the inductance, right? We take it for granted. Again, you should have learned it earlier in your elementary class, but it's okay you forgot because that's not the point. We are not important for this class. The important thing is that you know inductance determine how much voltage back EMF will be induced if you change the current. Okay, so let's look at the Josephson junction. Does it have an inductance? So first of all, V is equals to L. If I plug in the current, right? So this one, how to say this? So I assume, right? Assume it has inductance. Then V equal to di dt for this element. It's not an inductor, but it's a Josephson junction, right? It can turn out that this is undefined, right? But let's try if it works. What is I? I is IC psi phi dt. Right? I plug in the first equation. The current for Josephson junction is IC psi phi. Right? With this, then of course I know that I can take this out. This is equal to IC cosine phi d phi dt. So here I'm using the chain rule. I'm using the chain rule like this. D sine phi dt equals to d sine phi d phi dt. Okay, because the variable on top is phi, bottom is t, right? So d sine phi d phi is cosine phi, and then d phi dt. Then I continue. This is equal to L IC cosine phi. But I already know what's d phi dt. That is the second Josephson junction equation, Josephson equation, right? So that what is that? Do you remember? V divided by the reduced flux quantum. Yeah. So with this, the left-hand side is V, right-hand side has V. Then we say that EL is equals to 1 over IC cosine phi. Maybe I just put this on top right away. Phi naught dash. So it means that Josephson junction also have an effective inductance. Right? We first assume it has, but it turned out to work, right? Because any change of the current is going to induce a voltage, and the ratio is given by this. So we further define this. Define this as LC 1 over cosine phi, where LC equals to phi naught dash divided by IC, right? Or equal to phi naught divided by 2 pi IC. And this is called the Josephson inductance. So there are two things. One is that, Josephson junction does have an inductance. Why? Because its current and voltage relationship fulfill this law. And this L is equal to the reduced flux quantum divided by IC. It's pretty easy to memorize because in classical, you know, the flux is equal to inductance times the current, right? So IC times LC equal to flux. So that's how I memorize it. And second thing, which is even more important, is that this is the constant, but the total inductance is actually this constant divided by cosine phi. So this one actually depends on phi, so it is nonlinear. Later we'll look at that. Because of this nonlinearity, we can use it as a qubit, but we are not there yet. Any questions? Okay, if no, with inductance, then you probably will think about how about energy, because if you have an inductor, you plug in current, then you can store energy in the inductor. And the energy stored is as the form of magnetic field. But as we said earlier, we actually don't have magnetic field here. But we are going to store it as the kinetic energy of the Cooper pair, because it's superconductor, it keeps looping, right? But let's take a look how we derive the energy. First of all, what is the energy? Right? Energy is equals to the power. You integrate the power over time, right? And what is the power of a circuit? I times V. Okay? And we assume it go from phase phi 1 to phase phi 2 in this charging process. This is just like a capacitor, maybe just an inductor, right? You try to charge up the current. Then, of course, the energy stored there is equal to I times V dt. It's just the same. Okay? Okay, so with this, then we can plug in the Josephson equation. What is I again? Do you remember? What is the current going through Josephson Junction? The first equation? Thank you. I see sine phi. How about V? What is V in terms of phi? d phi dt times the reduced flux quantum, right? And then the whole thing d phi. Good. So we are pretty good now. Am I right? dt, sorry, not d phi. Okay, then the dt will get cancelled, right? So it's equal to what? I'm going to take out IC because IC is a constant. And then I'm going to take out the reduced flux quantum because it's a constant. And then the whole thing will be integrated from phi 1 to phi 2. And I have sine phi d phi. Right? Because this dt got cancelled, then d phi. They have sine phi d phi. Right? So when you integrate sine phi, what do you get? Negative cosine. Thank you. Negative cosine phi. Do I write it? From phi 1 to phi 2. Right? Which is equals to IC phi 0 dash cosine phi 2 minus cosine phi 1. But we actually don't care about the initial phase, right? We only care, yeah. Sorry, say again. Minus sign, but, oh yes, so it should be phi 1 minus phi 2. Thank you. I will just set, because energy, right, the most important is the relative. So I set phi 1 equal to 0, okay, and then phi 2 equals to phi. Then I get the energy equals to IC phi naught dash 1 minus cosine phi. This is the, and then I can try to make it into the quantum flux. So I, instead of reduce, so I put it as 1/2 pi. But you need to be careful when you read papers, right? Sometimes they put it as reduced flux quantum, sometimes they don't, okay? But the main point is that now I have the energy. You see the energy stored in this system, which is Ej, which is the Josephson energy, equals to IC phi naught divided by 2 pi, right? Or IC phi naught dash. Right? The current times the flux give you the energy. And you can also further show that Lj, the Josephson Junction, Josephson Inductance, equal to phi naught dash square divided by Ej. I always cannot memorize it, but just remember they have relationship. When you need them, just check the table. Okay, so we are done with the Josephson Junction. A little bit rushed, right? But what did we learn after all? We say that we have superconductor is zero resistivity plus Meissner effect. You need to have the temperature, E field, and the B field and critical current all smaller than the critical value. And more importantly, we say that for a superconducting device, the whole metal can be described by this macroscopic quantum object. And now the phase becomes important. When you have this Josephson junction, the phase is the difference between the phase of these two quantum objects, phi A, phi minus phi B. And with that, you have Josephson equation, first and second. And because it is nonlinear, we were able to get the Josephson inductance and also Josephson energy. If you forget anything, fine. But now I hope that you understand Josephson junction is just like an inductor, you learn in earlier classes. Okay? Because it's an inductor, it has inductance. It also stores energy. A regular inductance stores energy in magnetic field. Josephson junction stores energy in the so-called kinetic energy, the kinetic energy of the Cooper pair, because it's superconductor. They will keep running forever. Okay? And if you need equation, come back to find this equation. Otherwise, Josephson junction for you now is just an inductor, but it's a nonlinear inductor that you will find later. Or we will already show you it's nonlinear, and you find that it's useful very soon. Make sense? Should I continue or maybe just stop here? Only 5 more minutes. Yeah. No, then we need to quantize a circuit.